I want to share with you the macrocyclic ligands. Dear children, myself Dr. DIGNA VARGHESE. An area of particular research interest in recent years has been the construction of planar macrocyclic ligands. These are special types of polydentate ligands in which the ligating atoms are constrained in a large ring encircling the metal atom. A macrocyclic ligand is a macrocycle with a ring size of at least 9, including all heteroatoms, and 3 or more donor sites. Macrocyclic ligands exhibit a particularly high affinity for metal ions. These macrocycles have unusual property of forming stable complexes with metals. Therefore, macrocyclic ligands is a special class of chelating ligand, which includes that are the large ring compounds even without a metal atom present, and that can position several donor atoms inside their ring to donate to a metal ion. Such ligands are called macrocyclic ligand. Examples of macrocyclic ligand: polyether. Crown ethers are the major one under this category. In 1967, a new series of macrocyclic compounds was reported by Pedersen, who synthesized a number of cyclic polyethers or crown compounds. Polyethers in which the ether oxygen atoms separated by two methylene groups each lie in a nearly planar arrangement about the central metal atom. Here the central metal atom present, and the remainder of the molecule lies in a crown arrangement. Hence the name crown ethers. All of the oxygen atoms are pointed inward toward the metal atom. If this is a metal atom, inside the ether, crown ether, all the donor atoms, that is, here the potential donor atoms are oxygen, so these are pointing inward toward the metal atom, and these macrocycles have unusual property of forming stable complexes with alkali metals. This exceptional stability has been attributed to the close fitting to the alkali metal ion into the whole center of the ligand. Here we are representing some examples of crown ethers. Crown 5. Gas phase studies show that crown 5 prefers lithium ion more than the other alkali metal cations. Crown 5 prefers lithium more than other alkali metals, then lithium, next sodium ion, then potassium, and then cesium ion. Next one is crown 6. Crown 6 is more preferable for sodium ion, and then potassium, then lithium, then rubidium, then cesium. Cyclo-CH2CH2O 6 times contains 18-membered ring with 6 oxygen atoms as potential donor and is commonly known as 18 crown 6. Other one is crown 7. Here 7 oxygen atoms act as potential donors, and crown 7 prefers potassium ion more than sodium, than rubidium, than lithium, than cesium. Why we call it as crown 5, crown 6, crown 7, and so on. Crown is not because of its arrangement, that is its well-known arrangement like a crown. Okay, so crown 5 is that, means 5 is the potential donor atom number. after crown there is a number indicating the number of potential donor atoms. Here 5 oxygen atoms are present, so crown 5. In crown 6 there is 6 oxygen atoms are attached to the 2 methylene bridges, so it is crown 6. Crown 7 means there are 7 oxygen atoms attached to the methylene bridges and forming ether. And crown 6 also known as 18 crown 6. Why it is known as 18 crown 6? 18 means the total number of atoms. Here you can see, including the heteroatoms, here you can see one is this oxygen, and the second, third, fourth, fifth and sixth, seventh, eighth, ninth, 10th, 11, 12, 13, 14, 15, 16, 17 and 18. That is 18 means the total number of atoms and including the potential donor atoms. Potential donor atoms representing after crown, that is crown 6. Here 6 oxygen atoms. It is also written as 18 C 6. So it is 18 crown 6. In the case of crown 5, here 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So we can written as 15 C 5 and so on, or 15 crown 5. Okay, so 15 crown 5 is more preferable to lithium ions, and crown 6 is preferable to sodium ion, crown 7 is preferable to potassium ion. Properties of crown ethers. The difference in affinities of crown ethers shown in gas and solution phase suggests that solvent effects are quite important. Crown ethers have the unusual ability to promote the solubility of alkali salts in organic solvents as a result of the large hydrophobic organic ring. We know alkali metals do not normally dissolve in ethers as they do in ammonia, but they will do so if crown ligands are present. Okay. The ability to complex and stabilize alkali metal ions has been exploited several times to effect the synthesis that might otherwise be difficult to impossible. So here we can see a reaction. Potassium reacts with crown 6, 18 crown 6 in diethyl ether or tetrahydrofuran as solvent. We will get a alkali complex, metal complex, that is potassium crown 6 plus complex and electron. Okay. Consider a synthesis of two metals. Synthesis of a compound cesium gold or cesium. If you mix two metals, how do you determine that you do indeed have an ionic compound and not an alloy? Okay, when cesium was allowed to react with gold, the conductivity in this melt was characteristics of an ionic compound. Okay, first of all, this is an ionic compound. Its existence might be first appear to be improbable since it is an ionic compound between two metals rather than between a non-metal and a metal. We know ionic compound is formed from the metal and a non-metal, but this particular metallic compound is found to be ionic by its conductivity measurement. Okay. Further evidence was desirable. These methods such as non-aqueous electrochemistry and those showing the anomalously low SK value binding energy value, and the Mossberg chemical shift were used to characterize the compound. But this compound was synthesized or reported first Ronald. Unfortunately, Sir Ronald did not live to see his prediction was true. He was died in an automobile accident in 1971. Now we are discussing how this compound is synthesized. Two approaches were used. One is the solubility of alkali metals in liquid ammonia, the strong reducing power of the free electron, and the stability of the reduced species in this medium. Note that gold minus should be a powerful reductant. Okay. To stabilize metals such as sodium that might not otherwise react that ionization of any metal. Recall that the ionization of any metal, even sodium or cesium, is endothermic. Okay. To stabilize the metals such as sodium that might not otherwise react with macrocyclic polyethers to form sodium macrocycle plus gold minus salts. So these are two approaches. First one is solubility of alkali metals in liquid ammonia, and another one is to stabilize metals with macrocyclic polyethers to form crown ether complexes. We know ionization energy of cesium is 38939 and electron affinity of gold is 2.56. That is very much closer to the value of iodine. For iodine it is about 2.66. Okay. Alkali metals dissolve in liquid ammonia to give solutions of alkali electrolytes. From this reaction, metal reacts in ammonia to give metal cations and electrons. However, the situation is somewhat more complicated, would indicate, because the electrons can further react with metal to form alkali ions, that is M- ions. Thus, in general, there are alkali metal cations, okay, electrons, and also alkali anions in an equilibrium mixture dictated by various energetic factors. For example, that because of the excellent solvating of the electrolyte ion by in liquid ammonia for alkali metals, the alkali ions are not favored in these solutions and they are somewhat atypical. By using methylamine and ether solvents, we can use some amines and ethers as solvents like liquid ammonia, but by using these solvents with metals and also by adding solvents of low polarity such as N-pentane, the equilibrium can be shifted to crystals, and crystals sometimes grown. Okay, so these are not favorable or favored reaction for synthesizing compounds such as cesium gold. The affinity of alkali metal ions for crown ethers and cryptands causes cationic complexes to form readily in solution. For example, potassium reacts with crown ether 6 to in diethyl ether or tetrahydrofuran, forming potassium iron complex with crown ether and electron. Stabilization of the cations by complexation with the macrocyclic ligands allowed the isolation and determination of the structures of these compounds. When cesium reacts with excess 18 crown 6, that means a rough generalization can be made that excess ligand will favor the formation of the electrolyte in as much as all of the metal may be complexed as the cation. Okay, so cesium plus excess ligand, that is 18 crown 6, forming cesium cationic complex with electron. On the other hand, a mole ratio of 2:1 metal is to ligand tends to favor the alkalide. Here sodium anion is formed with a cationic complex with a crown ether. We know the sodium anion is the most stable and the cesium anion is the least one. So here with excess ligand we can complex like this, which can interact with the gold anion and forming the cesium gold ionic compound. We know gold electron affinity is almost similar to that of iodine. Okay. So stabilization of the complex by the complexation with macrocyclic ligands. Naturally occurring macrocyclic ligands, for example chlorophyll, that we all know. In this we can see a tetrapyrrole systems, that is forming a 4 nitrogen atom which is coordinated to the metal atom. Okay, in chlorophyll magnesia is the central metal atom. And another one is heme. Heme is also the same, similar to that of chlorophyll, that is porphyrin ring systems. It acts as a macrocyclic ligand, and in that substituents are different. Another one is vitamin B12. It is a corrin ring system and includes 4 nitrogen atoms like heme and chlorophyll, that is coordinated to the cobalt atom. In heme there is iron is the central metal atom. These all ligands, that chlorophyll, heme and vitamin B12, contain tetradentate macrocyclic ligands. The organic ligands of chlorophyll and heme contain a large 16-membered porphyrin ring that includes 4 nitrogen donor atoms. Okay, similar case as that of the vitamin B12. Here a corrin ring system which also includes 4 nitrogen donor macrocyclic ligand. Curtis macrocycles. In 1961, Curtis and House proposed the structure of the first macrocyclic ligand. A Curtis macrocycle is an organic framework which holds a transition metal iron via nitrogen atoms with varying substituents on the carbon atoms. Here you can see a Curtis macrocycle. Here the nitrogen atoms which holds the transition metal nickel here with varying substituents on the carbon. These Curtis macrocycles are formed from the reaction of transition metal with diamines complexes with acetone in a 2+2 condensation reaction. Another important macrocycle is phthalocyanine, written as H2PC. A large aromatic macrocyclic organic compound with the formula C8H4N24H2. Here you can see the structure of the phthalocyanine ligand. It is a blue compound. It is composed of 4 isointol units. Isointol unit is given here, and phthalocyanine composed of 4 isointol units linked by nitrogen atoms, that you can see from this structure. Phthalocyanines function as planar tetradentate dianionic ligands that can bind metals through 4 inwardly projecting nitrogen atoms. Here 4 inwardly projecting nitrogen atoms is one is this, one is this, and one is this, and one is here. The most important phthalocyanine complex is copper phthalocyanine, and the 4 nitrogen atoms attached to the copper and the 2 hydrogens are replaced and forming a strong bond. Phthalocyanines are structurally related to other tetrapyrrole macrocycles such as porphyrins and porphyracines. porphyrin structure we know, and porphyrazine structure is shown here. Halogenated and sulfonated derivatives of copper phthalocyanines are commercially important, which are used as dyes. Several applications of phthalocyanines which act as dyes, and most common dyes are its halogenated and sulfonated derivatives that are prepared when copper phthalocyanine treated with chlorine, bromine or oleum. Okay, and it is also used as pigments, and in catalysis it is used, and also act as organic solar cells, and in photodynamic therapy also it is used. Cryptands. Cryptands are a family of synthetic bicyclic and polycyclic multidentate ligands for a variety of cations. Cryptands are macrobicyclic, macrotricyclic, etc. and so on. Compounds generally having nitrogen atoms at the bridgehead positions, having sufficient space within its cage structure for polydentate ligation to metal ions or other cationic species. The complexes formed by cryptands are called cryptates. The most common and most important cryptand is NCH2CH2O, CH2CH2O, CH2CH2 thrice N, that you can see in this picture. So cryptands are macrobicyclic or tricyclic and so on. This compound is a bicyclic one, and the polyethers are attached by two nitrogen atoms at the bridgehead position. There is enough empty space within its cage structure for polydentate ligation to metal ions or other cationic species and forming complexes, that is known as cryptates. Cladrochelate or cryptate. Encirclement of metal ions by the ligand is shown by encapsulation reactions, in which the ligand forms a three-dimensional cage about the metal. These are called football ligands. Cryptands are also known as football ligands. Example that we are already seen: NCH2CH2, OCH2CH2, OCH2CH2 thrice N, that is shown here. Because of the polyether bridges between the two nitrogen atoms resemble the seams of a football, so it is known as football ligands. Ligands of this type form exceptionally stable complexes with alkali metals and show high selectivity when the size of the football is adjusted to fit the desired cation. Here we can see two complexes of cobalt, that is cryptate. Boron atoms form the apexes of on lower left and right, upper right coordinate positions on the octahedron are occupied by nitrogen atoms. Boron atoms form apexes on lower left and upper right coordinate positions are on the octahedron are occupied by nitrogen atoms. Here other example: cryptate derived from dimethylglyoxime, boron trifluoride and with the cobalt atom. Sepulchrate ligands. It is closely related to the football ligands. The sepulchrate ligands can be formed by the condensation of formaldehyde and ammonia onto the nitrogen atoms of tris-ethylene diamine cobalt 3. Here we can see the structure of the sepulchrate complexes These complexes, both cryptate and sepulchrate complexes, in sometimes known as cladrochelate complexes. In coordination chemistry, cladrochelates are ligands that can encapsulate the metal ions. Chelating ligands bind the metals more strongly than related monodentate ligands, and also the macrocyclic ligands bind more strongly than the typical chelating ligands. So it follows that bi or polymacrocyclic ligands would bind to metals particularly strongly. So therefore, cladrochelates are usually derived from bimacrocyclic ligands. Here we can see a structure of a cladrochelate complex, cobalt sepulchrate 3+. Other macrocycles are a molecular knot, which is a mechanically interlocked molecular architecture that is analogous to a macroscopic knot. Naturally forming molecular knots are found in organic molecules like DNA, RNA and proteins. Here you can see a molecular knot, that is a crystal structure of a molecular trefoil knot with the 2 copper 1 templating ions bound within it, which was reported by Jean-Pierre Sauvage and co-workers. A catenane is a mechanically interlocked molecular architecture consisting of 2 or more interlocked macrocycles, that is, a molecule containing 2 or more intertwined rings. The term catenane derived from a Latin word catena, meaning chain. A rotaxane is a mechanically interlocked molecular architecture consisting of a dumbbell-shaped molecule which is threaded through a macrocycle. Structure of rotaxane that has a cyclobis paraquat paraphenylene, which is a macrocycle just like a dumbbell shape. So these are some examples of macrocycles. Thank you for attending this video lecture.